Okay, hi. I hope I can keep you awake for most of the time. So basically, this is a joint work with Colin here, Adi Shamir, and Achior Weigretan. I will take my clicker now. Okay. So the insecurity of IoT devices is all over the news, and every day we hear more and more attacks going on. But most of these attacks simply view these IoT devices as poorly protected computers with an internet connection. For example, using default passwords and Linux BusyBox in the recent Mirai attack. So we decided to look at threats that are more specific to IoT devices, and we tested the security of the highly popular Philips Hue smart light system. We chose this system because it's based on a relatively mature technology with standards that are already undergone several revisions, and it's a relatively simple system to implement. It is a high-end product, and a large company really put a lot of effort into securing this system. Okay, so Zigbee is one of the biggest industry standards for IoT, and Zigbee Lightlink, or ZLL, is its standard used for lighting products. And a typical home installation includes several light bulbs that can communicate with each other and a controller over this ZLL wireless protocol in something called a personal area network, or a PAN, which uses encryption with a unique key to protect the communication. And the controller can be either a very simple wireless switch or a bridge that connects to the secure home network, and from that it's connected to the internet and can be controlled by a smartphone app. And then the user can turn the lights on and off, change the color, and other stuff that's supposed to be very, very cool. Okay, so we tested the idea of creating a worm, which basically spreads between lamps using only the standard Zigbee wireless protocol. And to do that, we need to overcome two main obstacles. The first one is how to take over a pre-installed light that resides in a different PAN with an unknown encryption key. And after we are able to do this, we need to find a way to cause this light to spread the infection and attack its nearby neighbors. Okay, so to start the work, we try to reverse engineer the system, break some lights physically, and then connect to and see how it works from the inside. So the first part is taking over pre-installed smart lights. And as we said before, all communication inside the PAN is encrypted using a unique encryption key. And there is a protocol that allows the controller to cause a lamp to join its network and send the encryption keys. However, we need to find a way to stop a malicious neighbor from stealing our lights away from us and controlling them. We don't want him to turn off the light in our bathroom in the middle of the night. So ZLL implements something called a proximity test. The lamp basically measures the signal strength of the first protocol message, and only if the signal is strong enough, indicating that the controller is in a very close physical proximity, it accepts the message and answers it. Otherwise, the message is discarded. So if we look at the outline of this protocol, the controller sends something called a scan request. It includes a randomly generated transaction ID that basically identifies this session of the protocol to the rest, with the rest of the messages. The lamp does the proximity test, and if it passes, it answers with a scan response. And after that, the controller can send different kinds of messages, either to make the lamp join the network or to reset to factory new, and there are more type of messages. So we needed to find a way to overcome this proximity test because we want to do this attack from a long range. So we looked at the specification of the reset to factory new message, and we saw that this message only contains one 32-bit random number. It's the famous transaction ID. But unfortunately for us, we can't set a valid transaction ID because of the proximity test, and we are too far away. So we looked at the small print of the specification, and we saw that this number is supposed to be a non-zero random number. So we asked ourselves, okay, and what if it is 0? So we looked at the implementation, and basically what we've seen that the lamp has a struct that it saves the transaction ID from the first message, and then on the next message received, it simply checks if this new transaction ID matches the one that it stores in memory. And I think that you can already guess what is the default value in this struct. It's, of course, 0. So basically, our very sophisticated attack is this protocol. We simply send one factory reset message with an ID 0. The light restarts, deleting all of its keys. And then when it wakes up, it goes into a backward compatibility mode to an older version of the protocol that doesn't do this proximity test, and so we can take over the lights. After we tested this attack in our lab, we decided to do something a little nicer. So we bought very cheap and lightweight transceivers. It cost a few dollars and weighs about 20 grams. And we decided to try to put it on a drone and attack a nice office building in Beersheba. It hosted a few relatively famous security companies and also the Israeli CERT. And as you can see in this video, the building is relatively far away. And this is the drone. The autonomous attack kit is hung by a USB cable underneath the drone. And as the drone takes off, you can see already in the distance the light starting to flicker. This is about 300 meters away, or as I understand, about 3 football fields. And as we get closer, we can start the second phase of our attack. After we send the factory reset message, we cause those lights to join our own new network. We take control over them. And now, for the people here that are familiar with Morse code, you can see that the lights are signaling SOS, rescue me. They have been taken over, and our attack is done. So basically, we have the first gadget of our attack. We can take over lights from really long distances. And now we need to go to the second phase. OK, so we now looked for a way to run code on the lamp. But it's a relatively big challenge for us, because those lamps use, the CPUs in those lamps are Harvard architecture, and they have really good source base. And it was very hard to try to exploit it. So we decided to try and misuse an over-the-air update mechanism that Philips put into those lights, and use them to spread our malicious code. So we tested these capabilities, and we found out that, unfortunately for us, those updates are encrypted and signed by Philips. But more fortunately for us, they use only symmetric keys. And they use the same symmetric keys in all the lamps from a specific model. So why did they do it? They did think about security. So the keys are stored inside a secure system on chip that are protected against debug and read from the outside. So there's no easy way to extract those keys. So we decided to try and use power analysis to extract the keys from the lamps. This is the setup that we used. So the first part was basically reversing engineering this whole software update. It starts from the files that, and the structure, but we didn't even know what kind of cryptographic primitives were used or what mode of operation. So we did correlation power analysis with a ciphertext, and to help us to understand how this data is manipulated. And from that, we could deduce that Philips chose to use a mode of operation called counter with CBC MAC, or CCM, which is also used in Zigbee. So now we know what the mode of operation, and the primitive, not so surprisingly, is AES block cipher. So we want to break it. So if we try to look what this CCM mode is made of, it's made of a stream cipher that encrypts a nonce and an incremented counter to generate the stream cipher, and then XORed to the ciphertext. After that, this decrypted plaintext is verified using CBC MAC. And unfortunately, again for us, this mode of operation is relatively hard to attack using side channels. And the reason is that unlike simpler modes like ECB, we don't have any direct control over the input to any of the block cipher operations. So we looked at the literature, and there were previous attacks on CCM. The first one requires 2 to the 16 blocks of encryption to break the scheme. And unfortunately for us, the firmware size was limited to the 14. So no luck there. And a more recent attack used a chosen nouns attack, an attack against the stream cipher, but we didn't even know what the nouns is. So our main observation was that instead of trying to attack this stream cipher, which is very hard, we'll try to attack the verification part instead. And if we look only in this CBC mark verification phase, then we can see that the input to the block cipher is a XOR of 3 values. The first value is the CBC state from the previous block, the stream cipher generated for this specific block, and of course the ciphertext. But if we take a closer look, we can see that the first 2 values are not dependent at all on the ciphertext that we input. So basically, we can view it as a ciphertext stored to some const per block, and then in ECB operation. Again, this can be simplified by simply incorporating this constant into the first round key of the AES. So now we have a very easy to attack scheme, an ECB scheme, and only with a modified key. And this modified key we can attack and extract, and from that we can deduce the original key. And CCM reuses its keys between verification and encryption. So we get both keys for free. And now we are able to sign and encrypt our own malicious updates. So we did also a small demo for that one. So go over to Colin.
Actually, we're able to do this. We have this really simple demo here. These are 3 Philips Hue light bulbs that were purchased new, and then we've done over-the-air updates. The firmware that we're running on them now, we've built from source code, so they're not limited to doing just features within the original code base or anything like that. And rather than doing something really evil, I've made a slightly annoying light bulb. This is what we decided to do. So you can see it blinks on and off. If I turn another light on, it steals control from the other light. So if we wait for another one to turn on here, it's random, so also it could be here a while. There you go. So if you turn this one on, and if I keep trying to switch them, you can see it always keeps only one bulb on. Oops, I missed that one. And it's doing this directly communicating with each other. So as soon as the bulb turns on, it sends a message that will turn others around it off. It's set multicast, so sometimes they get jammed and miss each other's messages, but mostly it works. So this is just a really simple, annoying light bulb example, but there's a few other demos that Elliot can talk about as well here.
Yeah. So now that I hope that we convince you that this worm is possible to make, we want to see, okay, so what is the meaning of that? So we wanted to see if we can create a worm that spreads, and it does. And now what are the effects? So we look at it as a little bit of a new type of an attack, which is dependent on the density of devices in the area. Because we need some critical mass of density to allow this worm to spread over large areas. And this is very known percolation theory techniques. We did a back of the envelope calculation for the city of Paris. And we saw that we need about 15,000 randomly located lights for this worm to spread over the entire city, which we found relatively low in number. So the attack simply starts by taking one malicious light and plugging it in anywhere in the city. From that, it can spread using this Zigbee protocol. And the nice thing about it is this protocol is not monitored in any way. It's really hard to detect that something is going on, and it's really hard to find the source of this infection. And because we go around any IP defense mechanism, all of the regular protection that we have is not going to help us. So what we can achieve with this attack? So the simple thing is we're going to do a widespread blackout, close all of the light in the city. But a nice thing about it is that when we attack those lights, we can permanently break them. There's no way to fix them afterwards. If you want to turn the lights on, you need to go physically replace this light and put a new one instead of it. It might be nice for the LED salespeople, but it will take quite a lot of time to get over this. And we can do more fancy stuff. For one example, we can cause very unusual loads on the electric grid and try to attack the electric grid itself. We can cause epileptic seizures in people that are photosensitive, and it's a very tough problem for someone that's in this situation and the entire city is blinking. And because Wi-Fi and Zigbee share the same radio frequencies, we can also jam Wi-Fi in a very large area. We are responsible people, so we did responsible disclosure. And we talked with Philips, and we disclosed all of the vulnerabilities a few months before we published. And the protocol implementation bug was actually fixed using the same software update mechanism that we attacked previously, which is nice because it is a security mechanism. Unfortunately, wasn't secure enough. Currently, the software update process is still vulnerable. Okay, so if we try to look at what went wrong in a more high-level view, with this IoT revolution, we're going to put billions of tiny transmitters all around us. And those tiny transmitters have the ability to create small ad hoc networks. But these ad hoc networks can be converted maliciously to very large area networks and create a new communication medium. This communication medium is currently not monitored and not protected in any way. And we need to find ways to make IoT devices that are more secure, but also secure this new medium that we are creating. Okay, and that's it. Thank you very much.
Thank you. Let's thank our speaker. Thank you. Okay, are there any questions? Well, you think your question. Oh, Peter.
I'm an SRI. Many years ago, when I was a kid, there was a movie by Charlie Chaplin in which he was a glazer. He went around fixing broken windows, and he was hiring all the kids to break the windows so that he'd have business. I'm wondering here whether one should go out and invest in Philips, because if you guys are loose breaking all of the windows in a particular city, that's purely apocryphal. The real question is, if you were designing the Internet of Things to assure that you had smart light bulbs that were adequately protected, and you were working, say, with Philips, what would you do?
I think the first thing is to, the main problem was in the threat model, because they did put a lot of effort in defending the system, but for example, the threat model didn't consider anyone extracting the keys physically out of the lamp. We did it in side channels attack. I'm sure there are ways to just connect it to the chip with more violent method and retrieve those keys. And actually, Zigbee supports OTA update is specific to each light. So they could use different keys, but it wasn't in the threat model. And I feel that if you look at the way that the Zigbee protocol was created, it was a closed industry protocol and didn't include any outside security advice. And I feel that if it will be done in a more inclusive way, we can make much better protocols that will have lesser probability of being implemented wrongly, and help to make a better threat model that we can actually protect.
Another question?
Hi, Federico Maggi, Trend Micro. Have you looked into Z-Wave by any chance?
I just seen today that they opened the specification a while ago, so not yet.
Because I think there might be, similar
I will assume so.
Yeah, thanks.
All right, thank you. Thank you again, speaker.